Okay, I want to analyze some certain special situations that arise a lot when you're thinking about linear dependence and independence. So I want to go through some special cases, but first, let me just remind you from the last video, we had this characterization of linear independence. Because this is going to be the one that makes it sort of easy to analyze. This characterization makes it easy to analyze special cases. So, because everything's going to come down to pivots, as it sort of always does. All right. So our characterization was if we have a matrix and we think about the columns as vectors, right? So the column vectors of a matrix A are linearly independent, if and only if every column is a pivot column. Right, that we sort of said, okay, there's this formal definition we give, but it basically, comes down to having no non-trivial solutions of the homogeneous system AX equals 0. Having only the trivial solution means that you have no free variables. Every column is a pivot column. So that's the idea. All right, so let's analyze some special cases using this to make our lives easier. So here's one, two vectors. Actually, let me say two non-zero vectors for now, because those zero vectors are going to be a different special case. So if you have two vectors, how do you tell if they're linearly independent or not? So v1 and v2. Well, what you do is you think about the matrix whose columns are v1 and v2. So we have A, which is this matrix. Columns are v1 and v2. Can even, if I want to do something like the following, sometimes I put a little dashed line, dotted line, just to say like, okay, these are two columns, they're both vectors. Okay, so, and there's two options, right? There's two options when we reduce this. The first option is that we get two pivots. We can't get no pivots because we're assuming these vectors are non-zero. So the two options are A, excuse me, we get two pivots. And so that means that the matrix, the reduced matrix, looks something like the following, right? So we get two pivots. And in this case, then they're linearly independent, right? Then this set, or these two vectors are linearly independent. Okay. And then the second case is that we get only one pivot. And that looks something like this, right? When we just have one pivot, this is what the reduced matrix looks like. But if you think about it, that means that V2 is actually a multiple of V1. So first, that means linearly dependent, right? Because not every column is a pivot column, just based on the characterization at the beginning of the video. So linearly dependent. But moreover, we can see that V2 is a multiple of V1. Or vice versa. Again, they're both non-zero vectors. So if V2 is 3 times V1, then V1 is 1/3 times V2. Okay. And so that's actually the point. The point is that basically, if you have two vectors, non-zero vectors, they're linearly independent if and only if one is not a multiple of the other. So let me just write that down. So the conclusion. Non-zero vectors v1 and v2 are linearly independent if and only if one is not a multiple of the other. So if you're looking in 2 or 3 dimensions, you basically want to just check if the vectors point in the same direction or not. And the same direction could mean opposite direction because one could be a negative multiple of the other. Okay, so that's it. So that's pretty easy. You're just basically saying, okay, like, this is the conclusion. All right. That's special case, the first special case I want to look at. So the next special case I want to look at is, what if you have the zero vector? The zero vector is in the set, is in your set of vectors. Zero vector is kind of a dumb vector. It's kind of a dumb vector, but you know, it does come up in certain situations. And my claim is that basically, if the zero vector ever shows up, your set of vectors is linearly dependent. So in this case, and I'll give a justification, but in this case, the set is linearly dependent. And you can see why. For example, if let's just say we had our matrix was something like V1, V2, V3 is the zero vector, and V4, right? If we row reduce this, the third column will still be 0, right? If you do row reduction operations, all you're doing is, you know, adding things vertically or multiplying things, and a column at 0 stays 0. So it remains a 0 vector. And that means that it's not thus it's not a pivot column. It's not a pivot column. And therefore, the set's linearly independent because linearly dependent, sorry. The set is linearly dependent because not every column is a pivot column. That's the reason why. So I guess this is the conclusion up here. Anytime you have the zero vector involved, the set is linearly dependent. An even goofy special case of this is even just the set just containing the zero vector. If you just have one vector, most of the time, one vector, if it's a non-zero vector, is that set is linearly independent because you can't. It's a pivot column, right? When you reduce one column, if non-zero entries, it's a pivot column. So even just this set is linearly dependent. And the reason, and you know, you can even go back to the definition, right? The definition is that you're supposed to write this linear combination of the vectors equals 0 and say that there's some non-zero scalars that make it true, right? But in this case, from the definition, x1 times 0 is true. It doesn't force x1 to be 0. It's true for x1 not 0. Like say x1 equals 1. And so this is a linear dependence. This, like, or maybe I should say 1 times 0, the 0 vector equals the 0 vector is a linear dependence relation. A dependency, I guess, is what I would call it in another video. Kind of silly, but still, we consider that to be linearly dependent. Okay. All right, so that's the second case. And then the third case I wanted to mention is what if you have more vectors than entries or dimensions? Dimensions. So here, so say we have a set v1, v2 through vn, and each vector, each vi lives in Rm, and m is greater than, no, less than n. I want more vectors than dimensions. So just for example, n equals 5 vectors and m equals 3 dimensions. Well, what's going to happen then? When we row reduce, so if we have this situation and we write it, you know, our set of vectors, being tricky here. If we write our matrix whose columns are these vectors, this will row reduce, and it has more columns than rows. There's at most one pivot in every row or every column. So, so even if there's a pivot in every row, there will not be a pivot in every column. Every row, we won't, no matter what, we won't have a pivot in every column. Thus, the set is linearly dependent. Dependent, right? Okay, so yeah. So I guess maybe I'll just make a statement that I can put a box around. When there are more vectors than dimensions for the vectors to live in. And hopefully your intuition for sort of what linear dependence is matches this, right? If I have three vectors in 2 dimensions, then definitely the third vector or one of the vectors has to be a linear combination of the other 2, right? There's no way to sort of like, it's almost like each vector, if you want them to be linearly independent, need to sort of span more and more space, right? Like the second, like the first vector, the second vector will either be on the same line or not, which will make it span, you know, either the 1 dimension or 2 dimensions. If it just spans the 1 dimension, you're automatically linearly dependent. If it spans the 2 dimensions, if the 2 vectors span the 2 dimensions, then the third vector definitely is going to be in that span. So it's going to be a linear combination of the first two. This is the kind of logic you can go through. Okay. And it also is nice just to think like if I have 43 vectors in 38 dimensional space, then I know those vectors are linearly dependent without actually having to compute anything. So that can be useful too. All right, I will stop there.